Okay, so here we are, section 8.2, the Pythagorean theorem and its converse. This is going to just be one video. We'll take 2 days on 8.2. It's a big section. We really need to. But I'm going to do one video for it, and we'll just do like problems in class and homework and problems in class again. So I'll try to make it brief because I'm going to hit upon a lot of things in class. But you really should already know this because they make us do the Pythagorean theorem all year long, and then we use it to develop the distance formula. Now we're actually going to really formally go through it. And in class, I'll go through the proof of it. I'm just going to show you how to do it in the video. So first of all, things we have to identify. When you have a right triangle, the biggest side, that ends up being the hypotenuse, right here, hypotenuse. Other two sides are called legs. Okay, so biggest side hypotenuse, smaller sides legs, plus the hypotenuse is also always opposite of the right angle. So that's our other answer, other way to know hypotenuse. So the Pythagorean theorem, pretty classic here. In a right triangle, the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. So basically, a squared plus b squared equals c squared, and this is the key that you have to have memorized, I guess. C squared is c is the hypotenuse. Okay, yeah. So here's the first example, real quick. I'm going to ask you two questions. One is, what side are we solving for? A, B, or C? And then after we go through it and I'll show you, I'll ask you, hey, did this make sense? So here we go, real quick. After I get after this leaves, yeah, there we go. Answer A, B, or C. Okay, so hopefully you said that we're looking for side C because that's the hypotenuse. So let's go through and do the work on it. Okay, so um, 17, I don't know, it doesn't matter what we call it. We can just call it A. 7, we'll call it B. Okay, so that's C. So we'll have 17 squared plus 7 squared equals c squared, or actually, sorry, just call it x squared. So 17 squared, this chapter we get to use our calculators a fair amount, so I think it's 384. 384? No, it's not right. 389, if I remember off the top of my head right. Yeah, 289, sorry, 289. So 17 squared is 289. I'm doing this a little late, so I'm kind of tired. Plus 49 equals x squared. This ends up giving us, I don't know what, 339, 338, I think. Yeah, 338. And now to solve for this, take the square root of both sides to cancel it off. Now again, this chapter we are going back to simplifying square roots. So 338, if you say that as your answer, that's wrong. Okay, so it's easily divisible by 2 because it's even. So 2 gives me then, I don't know, 169. Yeah. And then hopefully you recognize that 169 is 13 times 13. So hey, I got a pair of 13s, so x is actually equal to 13 root 2. All right, so yeah, so the next question is going to pop here in a second of, did that make sense? Okay, so there are other things in the book that they bring up, and this is actually a section where, for me as a mental math person, as a lazy person, it took a little bit of energy and effort to memorize these in high school, but once I did and understood them, it's made a lot of things a lot easier. And they're called Pythagorean triples. And what Pythagorean triples are, oh, it says to define it, and I didn't put a definition in the notes here, did I? So Pythagorean triples, they are 3 side lengths. Can't type. That's our whole numbers. So they're not decimals, they're not fractions. So that last problem we did, where we got 13 root 2 for the hypotenuse, looking at all 3 sides real quick, that's a whole number, not a decimal, not a weird radical. That's a whole number, not a weird decimal radical. But x was 13 root 2, there's a radical with it, so it's not a Pythagorean triple. And the nice thing about Pythagorean triples is, which here are the classic ones, 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, 25, and 9, 40, 41. And what that means is if you have 3, 4, and 5 for side lengths, you know you have a right triangle. Obviously, 5 is the hypotenuse. The largest number is the hypotenuse. But what's great about triples is their multiples are also triples. So 6, 8, and 10, which are all 3 of these doubled, they're also triples, which means 6 squared plus 8 squared equals 10 squared. And triplet, 9 to 12 to 15, it works. Heck, even throwing variables in, 3x, 4x, 5x, they're all still triples. 5, 12, 13, and all of its common multiples or triples, 8, 15, 17, 7, 24, 25. And then the book leaves one out, which I'm just giving to you here for you to kind of sneak in. 9, 40, 41. This is also one that will occasionally pop up. And again, so would like 18, 80, 82, or 9x, 40x, 41x. So here's the beauty of triples. This problem here, I could do the Pythagorean theorem, but I'm going to show you how to do it without doing hardly any work at all. Okay, so yeah, so here we go on the next slide, or next paper, I should say. Okay. So I've got a 48, 20, and x for side lengths. Now here's how it works. What you do is you figure out what's the biggest number that either both of these can be divided by or some kind of weird common factor. So 20 and 48 can both be divided by 4. If I divide this by 4, I get 5. If I divide this by 4, I get 12. So now what I do is I go back, or if you memorize them once you get them down, and say, okay, do two of those sides, do they match any of our special triples? Well, they do. The 5, 12, 13, because again, 13 had to be the hypotenuse. Well, I've got two legs in my drawing. Okay, so the leg is 5, the other leg is 12, so that means this must be 13. But here's the real trick to this. It's not really 13. First of all, 13 is less than 48. That's smaller. Hypotenuse can't be smaller. But secondly, to get to these numbers, I had to divide by 4 and divide by 4. So to get to x, I'll have to multiply by 4, which is the opposite of that, which is 52. And that's because 52 over 4 is 13, and it matches our 12 or 5, 12, 13 triple. So right there, I was able to figure out the missing side is 52 without actually having to even do any Pythagorean theorem. And those were pretty good sized numbers. That would have been a pain in the neck to do without a calculator. Okay. So let's try another one then, 2b. Same idea. We've got 14 and 50. Okay, so I'm going to give you a second to try it yourself and throw what you think the answer is up there, and then yeah, I'll go through it. Okay, so again, we're looking to see, what do we have? Well, I have a leg and I have a hypotenuse. So here's the deal. I have both these guys here. I'm looking for another leg. Well, again, look for the biggest thing they're both divisible by. Both divisible by 2. This guy is 7. This guy is 25, and the question is, do I have a triple that has 7 and 25, with 25 being the hypotenuse? And the answer is yes, I do. I have a 7, 24, 25 triple. So I've got the 7, I've got the 25, that means this guy is the 24. But how did I get to these two sides to go backwards? To break it down, I divided them by 2, which means this guy needs to be doubled to multiply by 2. So there's 48. Okay, now the last theorem for this section, it's actually a three-part theorem, but it's really just one theorem. And when we go over it in class, I'll always think of it as one theorem. So the book calls it 3, the converse of the Pythagorean theorem, and that is that if you have a right triangle, or if you have a triangle and a squared plus b squared equals c squared, you know it's a right triangle. Remember, converse flips it. So if we knew it's a squared, if we knew it's a right triangle, we know a squared plus b squared equals c squared. Well, if we try to do the Pythagorean theorem and a squared plus b squared equals c squared, hey, that was a right triangle to begin with. Now, the next two theorems then go back to this, and they do the relationship of, well, what if a squared plus b squared doesn't equal c squared? So here's the first one. This one says c squared is less than a squared plus b squared. Now what you have to realize is, in order for that to happen, that means that this side here, a and b, if we keep those the same, only way c squared could be less is if c itself got smaller. So let's say we shrank c. Well, then what happens is, whenever I draw this in, I go from now, this side here is still a in length. This guy here is still b in length. Oh, c got smaller, and now I don't have a right triangle anymore. I have an acute triangle. Now the other part of it says, okay, well, if c squared is bigger than a squared plus b squared, it's obtuse. And what's happened here is, if we keep a and b the same size, if we make c squared larger, that means that c had to be larger. What ends up happening is this door opens up more. So if you think of it as like a door, hey, I closed the door, that's when it became acute, and c squared was smaller than a squared plus b squared. If I open the door, that means c's gotten bigger, which means c squared got bigger, therefore it's obtuse. Okay. So we're just going to look at a couple examples. Okay. The first one here is 11, 60, 61, and the question is it obtuse, acute, or right? Okay. So let's go to our problem. Whoops, don't need that menu. Okay. So 11, 60, 61. Now the thing is this, it's obvious, there's the hypotenuse. It's the biggest side. So let's try 11 squared plus 60 squared and see how it compares to 61 squared. Okay. So 11 squared is 121, 60 squared is 3600, 61 squared, I don't know that off the top of my head. I don't feel like trying to figure it out. So get out the calculator. I know it's going to end in a 1. (61 squared is 3721). Okay, so now we add 121 and 3600. Well, that ends up being 3721. So do those two guys equal? Yeah, they do. That means then this is a right triangle. Okay. And anytime you're doing one of these problems where it asks you to check, is this a Pythagorean triple, you have to, or is this a right triangle, acute or obtuse, I need to see this work. You can't just say right triangle, acute. I need to see that you tried it out. Okay. So we'll see. And again, next question to pop up will be, well, did this make sense? And hopefully you say, yes, it did. Okay, so let's try 4b. Now 4b is trickier, not really because of the fact that it's that much harder, but what it is it's the algebra or the arithmetic behind it. Now, you might not know ahead of time, hey, which one's the hypotenuse? So I got a 4 here, so I think this is the biggest side, but I also see a 3 here and a root 5 there. I don't know which one's bigger. Well, here is the key to this one. You're going to square all these guys anyway, regardless. So, when I square a radical, what that means is I square both parts. I square the 2, and I square a square root. And one of the things you should have learned in Algebra 1 is if you square a square root, it cancels it off. So I get 2 squared, which is 4. Square root of 3 squared is 3. That's 12. Okay. Do the same thing for the other two. 4 squared, root 2 squared. Again, cancels that off. 4 squared is 16. 16 times 2 is 32. And then I have 3 root 5 that I'm squaring. Well, 3 squared is 3 squared, and root 5 squared is root 5 squared. That cancels off the radical. 3 squared is 9. 5 squared is, root 5 squared, sorry, is 5. 9 times 5 is 45. So that was the biggest one squared, meaning this had to have been C to begin with. So I could call either of these B or A. Now, I could check it, and that's what I'm going to do now is check with the converse of the Pythagorean theorem. So I'm going to do A squared, because that's what this guy is, plus B squared, and see how it compares to C squared. So 12 plus 32, and then 45. When I add these two up, 12 and 32 is 44. This is 45. Oh, these are definitely not equal. A squared plus B squared is less than C squared. So if we go back to our theorem, what does that mean? Well, let's see. A squared plus B squared is less than C squared, meaning this guy right here. And I know it's flipped, so if I flipped it around, it'd be C squared is, or A squared plus B squared is less than C squared here. Oh, this guy is obtuse. Okay. Obtuse triangle. Okay. So again, sorry, this is a little longer than I meant for it to be, but again, there's a lot of stuff, and we're going to spend a couple days on it, so you don't have as much homework to do video-wise. Okay, so yeah, if you've got any questions, come in after class or before school and we can talk. Thanks.